There exists a colossal gap in our understanding of the universe around us. This gap spans approximately 1/5 of the observable sky, and astronomers have given it a rather ominous name, the Zone of Avoidance. Throughout most of the modern astronomical era, this vast region remained essentially unmapped because the dense concentration of stars and interstellar dust within our own Milky Way galaxy creates an impenetrable barrier to observation. The situation becomes particularly intriguing when you consider that our entire galaxy is being drawn toward this obscured region at velocities approaching 600 kilometers per second relative to the cosmic microwave background. The fundamental principle of physics tells us that gravitational attraction requires the presence of mass. Therefore, we could deduce with certainty that something absolutely enormous must be concealed within that blind spot. Yet when astronomers pointed their optical telescopes toward this region, they encountered nothing but an endless expanse of darkness. Recently, however, we have developed the technological capability to penetrate that cosmic veil. What scientists discovered lurking behind it represents far more than a random assortment of distant galaxies. Instead, they found a critical missing component in the grand gravitational puzzle that governs the motion of our galaxy and our local cosmic neighborhood. To fully comprehend what has been hiding in this mysterious zone, we must first examine why this particular region of space remained invisible to us for such an extended period. When you examine a three-dimensional reconstruction of our local universe, a very distinctive pattern immediately becomes apparent. The overall configuration resembles an hourglass standing upright. Or perhaps it brings to mind a butterfly with its delicate wings fully extended. You can observe a dense concentration of galaxies forming a fan-like structure that extends outward toward the northern celestial hemisphere, while a second similar fan of galaxies spreads toward the southern celestial hemisphere. However, at the precise location where these two expansive fans converge in the central region, there appears to be absolutely nothing. This peculiar hourglass shape manifests itself in virtually every comprehensive redshift survey that astronomers have conducted over the past several decades. The visual impression suggests that we are positioned at the center of two vast cones of astronomical data that are separated by a dark, apparently empty band wrapping around the middle like a belt. This appearance of emptiness, however, represents nothing more than an optical illusion created by our specific vantage point within the galaxy. Cosmologists operate under a fundamental principle known as isotropy. This concept embodies the idea that the universe should appear roughly uniform, regardless of which direction you choose to observe. If you were to carefully count the number of galaxies contained within a specific patch of sky on your left side and then perform the same counting exercise on an equivalent patch of sky on your right side, the numerical results should be approximately equal. The large-scale architecture of the cosmos does not exhibit any preferential orientation or directional bias. Consequently, when we examine maps that display a gigantic gap slicing directly through the middle of our observations, we understand immediately that this gap does not represent actual reality. The galaxies exist in that region. We simply lack the ability to detect them and place them accurately on our maps. Astronomers have wrestled with this observational problem for well over a century. The specific term Zone of Avoidance was actually coined as far back as 1878 by an astronomer named Richard Proctor. He was meticulously studying distribution maps of nebulae, which we now understand to be distant galaxies far beyond our own Milky Way. During his analysis, he observed a pronounced decrease in the number of visible nebulae along the line corresponding to the plane of the Milky Way. For many decades following this discovery, the name assigned to this region was quite literal in its application. Astronomers deliberately avoided pointing their telescopes toward this area because it represented a frustrating waste of valuable telescope time. When observers directed their instruments toward the Zone of Avoidance, they consistently obtained messy, unclear data that proved difficult or impossible to interpret. They could see a handful of bright stars belonging to our own galaxy, but the background universe that lay beyond was completely washed out and rendered invisible. It functioned as a practical blind spot in our cosmic vision. The scale of this blind spot is far from trivial. It obscures somewhere between 10 and 20% of the entire optical sky, depending on how strictly you define the boundaries. That might initially sound like a relatively minor fraction, but when you consider the implications in terms of three-dimensional volume, the impact becomes truly massive. In practical terms, this means that for every 10 galaxies we successfully catalog and add to our cosmic census, there exist 1 or 2 additional galaxies hidden within this wedge-shaped region that we miss entirely in our surveys. This observational gap evolves into a genuinely serious problem when we attempt to understand our position and motion within the universe. Astronomers are engaged in an ongoing effort to map the flow of gravitational forces throughout our local cosmic neighborhood. We can clearly observe massive superclusters of galaxies exerting gravitational pull on our galaxy in one direction. But if there exists an equally massive structure hidden within the obscured wedge, then all of our calculations concerning galactic motion and gravitational dynamics will be fundamentally incorrect. We find ourselves essentially attempting to navigate through a room while wearing blinders that completely block our peripheral vision. We can see with reasonable clarity what lies directly ahead and what lies behind us, but our view of the sides remains frustratingly blurred. The reason we experience this significant blind spot has nothing to do with any peculiarity of the distant universe itself. The problem originates much closer to home. It represents a problem of observational perspective caused specifically by where Earth happens to be located within our galaxy. We live inside a spiral galaxy. The Milky Way possesses a shape similar to a flattened disk, not unlike a dinner plate resting on a table. It features a prominent central bulge at its core and elegant spiral arms that extend outward to the edges. Our solar system occupies a position embedded within this disk, approximately halfway out from the galactic center. This specific location fundamentally defines and constrains our view of the broader cosmos. When we direct our telescopes upward or downward relative to the flat plane of the galactic disk, our view remains remarkably clear. There simply is not much intervening material positioned in the way. We gaze past the relatively few local stars in our immediate neighborhood and look straight out into the depths of deep space. That is precisely where we observe the distant galaxies that populate our standard astronomical maps. However, when we attempt to look along the plane of the disk itself, everything changes dramatically. We are trying to peer through the main body of our own galaxy. It resembles standing in the middle of a dense, old-growth forest. If you look straight up toward the sky, you can see the blue heavens clearly above the canopy. But if you look horizontally through the trunks of the trees, your view becomes blocked. You might be able to see a few nearby tree trunks in your immediate vicinity, but you cannot see the landscape that lies beyond the forest. The trees obscure everything in the distance. In the context of the Milky Way, the trees in our metaphor are represented by stars, clouds of gas, and cosmic dust. The stars themselves are not actually the primary problem. Even though our galaxy contains billions upon billions of individual stars, space itself is so incredibly vast that we could theoretically look between them to observe distant objects. The real problem comes from what astronomers call the interstellar medium. The space between the stars is not truly empty, but is filled with extensive clouds of cold molecular gas and cosmic dust. This dust functions very much like thick smoke in the atmosphere. It consists of tiny particles composed primarily of silicates and carbon compounds. When visible light from a distant galaxy attempts to travel toward Earth, it inevitably encounters this dust. The dust particles absorb the light or scatter it in random directions. By the time that light finally reaches our telescopes, it has been attenuated to such a degree that it becomes so faint that it is practically undetectable by conventional instruments. Astronomers use the technical term extinction to describe this effect. In the central regions of the Zone of Avoidance, the extinction effect is severe and comprehensive. The Milky Way appears brightest and thickest when we look toward the galactic center, which resides in the constellation Sagittarius from our perspective. Here, the wall of interstellar dust becomes impenetrable to standard optical telescopes. For an extended period, we simply could not determine what existed on the other side. A massive galaxy could be positioned directly behind the Milky Way's dense core, and in visible wavelengths of light, it would be completely invisible to us. This physical barrier is precisely what creates the distinctive butterfly shape in our astronomical maps. The wings of the butterfly represent the clear views we obtain above and below the galactic plane. The empty body of the butterfly corresponds to the dusty disk of the Milky Way itself, blocking our direct line of sight. We could determine from gravitational measurements that something was pulling us toward the obscured region hidden in that dust. But we lacked the observational ability to see through the cosmic fog. We could not simply move the Earth to a better viewing location outside our galaxy. We were stuck inside, trapped within the disk. Therefore, to solve the frustrating problem of the zone of avoidance, astronomers had to fundamentally change their approach to observing the sky. The human eye perceives only a very narrow band of the electromagnetic spectrum. We refer to this restricted range as visible light. As we have discussed, interstellar dust blocks this type of light with remarkable efficiency. The dust particles measure roughly the same size as the wavelengths of visible light. When the light waves collide with the particles, they either bounce off in different directions or get absorbed entirely. But electromagnetic radiation comes in many other forms beyond visible light. If you increase the wavelength of the light, making it longer, it fundamentally changes how that light interacts with matter. The first major breakthrough in penetrating the zone of avoidance came with the development of infrared astronomy. Infrared light possesses a wavelength just slightly longer than the red light that sits at the edge of human vision. This slight difference in wavelength matters enormously because the longer waves can often slip past the small grains of cosmic dust with much greater success. It resembles the way that firefighters use infrared cameras to see through thick smoke in a burning building. The visible light gets blocked by the smoke particles, but the heat radiation passes through relatively unimpeded. Astronomers began systematically surveying the zone of avoidance using infrared telescopes. A key instrument in this effort is the VISTA telescope, which is located in Chile. This telescope scanned the sky to create a detailed map of the previously hidden region. In the infrared view, the thick wall of the Milky Way begins to become transparent. We can suddenly observe thousands of stars and galaxies that were completely invisible in optical wavelengths. However, even infrared light has its limitations. The deepest, most dense parts of the Milky Way remain too thick, even for infrared observations to penetrate effectively. To see through the absolute densest core of our galaxy, astronomers needed something even more powerful. They needed radio waves. Radio waves represent a distinct phenomenon from sound waves, despite the similar terminology. They constitute a form of electromagnetic radiation with very long wavelengths. While a single wave of visible light measures microscopic in scale, a radio wave can measure centimeters or even meters in length. To a radio wave, cosmic dust effectively does not exist as an obstacle. The wave is so large relative to the dust particles that it passes right over the tiny dust specks without being disturbed in any meaningful way. Radio waves travel through the Milky Way as if the space were essentially empty. This property allowed astronomers to search for a specific signal known as the 21-centimeter line. The universe is filled with hydrogen. It represents the fundamental fuel that makes stars shine. Almost every spiral galaxy contains rich reservoirs of neutral hydrogen gas. This gas naturally emits a radio signal with a wavelength of exactly 21 centimeters due to a quantum mechanical process involving the spin of electrons. This was the key that unlocked the zone of avoidance. Astronomers did not need to see the starlight from a hidden galaxy. They just needed to listen for its hydrogen. If they pointed a radio telescope at a seemingly blank patch of the zone of avoidance and detected a concentration of hydrogen gas, they knew with certainty that a galaxy was present there. Modern radio telescopes have refined and perfected this process. The Meerkat telescope in South Africa recently conducted an extensive survey of the zone. It possesses incredible sensitivity to radio signals. It found hundreds of galaxies in a small area that previously appeared completely blank. Crucially, these radio signals provide astronomers with more than just a location marker. They allow scientists to measure the Doppler shift of the galaxy. By carefully analyzing how the radio wave either stretches or compresses, we can determine how fast the galaxy is moving away from us due to cosmic expansion. This tells us its distance. Once we have the distance, we can place the galaxy accurately in a three-dimensional model. Bit by bit, these radio and infrared surveys started filling in the wedge. The zone of avoidance transitioned from being a complete mystery into becoming a detailed map. We realized that the universe did not stop or become empty behind the Milky Way. It continued on, rich and crowded with cosmic structure. Once the new data started flowing in from these radio and infrared surveys, clear patterns began to emerge from the noise. The points of light were not scattered randomly across the sky. They were grouped together in specific configurations. In 2016, a team of researchers led by René Kron-Korteweg announced a major discovery that fundamentally changed our map of the local universe. They found the Vela Supercluster. This structure represents a massive concentration of galaxies located approximately 800 million light-years away from us. In cosmic terms, that distance is reasonably close. It qualifies as a neighbor in astronomical parlance. The reason we missed detecting it for such a long time is that it sits directly behind the thickest part of the Milky Way's disk. If you look at the constellation Vela in the night sky, you are looking right at the location of this supercluster. But the dust in that particular direction is so dense that optical telescopes saw almost nothing whatsoever. When the radio data finally pierced through the obscuring fog, astronomers realized they were looking at something truly gigantic. Vela is not just a modest cluster of galaxies, it is a supercluster. This means it represents a collection of galaxy clusters bound together by their mutual gravitational attraction. To give you an accurate sense of the size, it spans an area of the sky roughly 20 degrees by 25 degrees. For comparison, the full moon that we see in the night sky is only half a degree wide. If we could see the Vela supercluster with our naked eyes, it would dominate a huge portion of the southern sky. It would appear as a giant glowing web stretching across the stars. The structure appears to be wall-like in configuration. It forms a dense sheet of galaxies and gas. Before we found Vela, astronomers knew about the Shapley supercluster. Shapley represents another massive structure in a nearby part of the sky. For a long time, scientists thought it was the main source of gravitational attraction pulling on our local group of galaxies. But the mathematics never quite worked out correctly. The gravitational pull from Shapley was strong, but it was not strong enough to explain the high speed at which our galaxy is moving through space. There was missing mass somewhere in the equation. Astronomers needed something else to be pulling us, something we could not see or detect. The discovery of Vela helped solve this puzzle. It provided the missing mass component. Vela sits in a similar direction to Shapley, but at a different distance from us. When you add the mass of Vela to the mass of Shapley, the gravitational mathematics starts to make much more sense. Scientists found a heavy weight on the gravitational scale that they didn't know existed. This discovery served as a wake-up call for cosmologists worldwide. It proved definitively that the Zone of Avoidance was not just hiding minor details or a few scattered galaxies. It was concealing some of the biggest discrete structures in the entire universe. We were trying to understand the dynamics and motion of the cosmos while missing one of the most important pieces of the puzzle. The Vela supercluster showed us that even in the modern age of astronomy, there are still giants hiding in the dark, waiting to be discovered. The Vela supercluster represented a major find in our understanding of cosmic structure. But it was not the end of the surprises hiding in the Zone of Avoidance. In 2020, astronomers announced the discovery of something even larger and more astounding. They called it the South Pole Wall. This discovery highlighted just how much of our local neighborhood remained unknown to us. We often operate under the assumption that the closest parts of the universe are the ones we know best. We map the solar system and the local stars within a few light years with tremendous precision. We presume that giant structures are things we only find billions of light years away in the deep universe. Relics from the early cosmos, the South Pole Wall proved that this assumption was fundamentally wrong. This structure is absolutely massive in scale, and it is positioned right next to us in cosmic terms. It forms a dense curtain composed of thousands upon thousands of galaxies. It stretches across the southern sky in a giant arc that wraps around a significant portion of the celestial sphere. The structure is so large that it spans approximately 200 degrees of the sky. To visualize that angular distance, imagine standing in an open field with an unobstructed horizon. If you look at the horizon on your far left and then turn your head all the way to the far right, you have covered about 180 degrees of arc. The South Pole Wall is actually wider than your entire field of vision from horizon to horizon. It sits roughly 300 to 500 million light years away at its closest point to us. On the scale of the observable universe, that is practically our front lawn. It represents our immediate cosmic neighborhood. The reason we missed such a gigantic object for so long is, once again, the Zone of Avoidance and the obscuring dust of the Milky Way. The wall wraps around the celestial South Pole in our sky. A significant section of it passes directly behind a region of the Milky Way known as the Chameleon Complex. This is a dense area filled with molecular clouds and dust that is actively forming new stars. It blocked the light from the galaxies behind it, breaking the arc and making the structure look like a series of unconnected pieces scattered across the sky. Without being able to see the full structure, astronomers could not connect the dots to realize these pieces were all part of one enormous cosmic wall. The way astronomers finally found this wall is absolutely fascinating and demonstrates the ingenuity of modern astrophysics. They did not just look for light or search for galaxies directly. They looked for motion and gravitational influence. Galaxies drift through space over cosmic timescales. Some of that motion is caused by the expansion of the universe itself, which pushes everything apart in accordance with Hubble's law. But some of the motion is caused by gravity. Galaxies are pulled toward areas with high concentrations of mass. By meticulously measuring the speed and direction of thousands of galaxies around us, researchers could create a detailed map of gravitational currents flowing through space. They call this phenomenon cosmic flows. It resembles mapping the currents in the ocean to find a hidden island. Even if you cannot see the island itself, you can observe how the water moves around it and deduce its presence. When researchers analyze these cosmic flows in detail, they noticed that galaxies in the southern sky were behaving strangely. They were moving in patterns that suggested a massive amount of matter was influencing their trajectories. The data pointed clearly to a large continuous filament connecting the pieces of structure we could see. When they reconstructed the map based on gravity and motion rather than just visible light, the South Pole wall appeared in its full glory. It connects to the Vela Supercluster, forming a vast web of matter that surrounds us. Its size rivals the famous Sloan Great Wall, which held the record for years as one of the largest known structures in the entire cosmos. This discovery fundamentally changed our picture of the local universe and our place within it. We are not floating in a random scattering of isolated galaxies distributed uniformly through empty space. We are enclosed by giant walls and filaments of matter. The zone of avoidance was the only reason we did not realize we were living in such a crowded and structured cosmic environment. We had been living in a house without knowing the walls existed around us. All of these discoveries lead to one main conclusion. They solve a fundamental physics problem that has bothered astronomers for decades. The problem centers on speed and motion. If you measure the movement of the Milky Way relative to the rest of the universe, you find that we are not sitting still in space. We are moving very fast through the cosmos. Our entire galaxy is rushing through space at about 600 kilometers per second. That velocity is incredibly fast by any measure. If you could travel at that speed, you could journey from the Earth to the Moon in approximately 10 minutes. The distance that takes spacecraft days to traverse would be covered in the time it takes to drink a cup of coffee. In space, motion like this is never random. It is always caused by gravity. If a galaxy is moving in a specific direction at high speed, it means something massive is pulling it through gravitational attraction. For a long time, astronomers knew the direction of our motion. We were heading toward the constellations of Hydra and Centaurus in the southern sky. But when they looked at the maps and tried to identify what was pulling us, the numbers did not add up. The visible mass did not match the observed motion. Astronomers could see a structure in that direction called the Great Attractor. It is a dense region of galaxy clusters that creates a significant gravitational well. For years, scientists thought this was the engine driving our motion through space. They assumed the Great Attractor was a colossal object pulling everything in the local universe toward it like a cosmic drain. However, as our measurements got better and more precise, we realized the Great Attractor was not heavy enough to explain our velocity. It had a lot of mass, certainly, but not enough to generate the speed we were observing. It was like finding a magnet that was too weak to pull a heavy piece of metal. The force did not match the effect. There had to be something else contributing to the gravitational pull. The zone of avoidance was hiding the answer. With the discovery of the Vela Supercluster and the mapping of the South Pole wall, the picture changed dramatically. We realized that the Great Attractor is not a single isolated object at all. It is merely the center of a much larger valley of gravity. We call this vast valley the Laniakea Supercluster. The name comes from Hawaiian and means immeasurable heaven. It is the watershed that contains the Milky Way and tens of thousands of other galaxies. But even Laniakea is not the end of the story. The new maps show that the gravitational pull extends even further than we initially thought. Behind the Great Attractor and partly hidden by the Zone of Avoidance lies the Shapley Supercluster. Shapley is a true monster of the local universe. It contains dozens of massive galaxy clusters gravitationally bound together. It is far more massive than the Great Attractor. The new data suggests that our motion is actually a combination of multiple forces acting on our galaxy simultaneously. We are falling toward the Great Attractor, but the Great Attractor itself is being pulled toward the Shapley Supercluster. The Vela Supercluster adds its own significant gravitational tug from the side. The South Pole Wall contributes to the overall gravitational landscape. The hidden region was the missing variable in the equation. Before we could see into the zone of avoidance, we were trying to balance the books with half the data missing. We could verify the speed of our motion, but we could not find the source of all the gravity causing it. Now that we can see the walls and superclusters hidden behind the Milky Way, the mathematics finally works. The mass in the hidden zone equals the gravitational pull we feel. We finally understand why we are moving in the direction and at the speed that we observe. It is like solving a mystery where the crucial evidence was hidden in a locked room. Once we got the door open, everything made sense. The implications of these discoveries extend far beyond simply filling in blank spots on a map. They fundamentally change our understanding of cosmic structure and evolution. The universe is not a uniform distribution of galaxies scattered randomly through space. It is organized into an intricate cosmic web. This web consists of dense filaments where galaxies cluster together, separated by vast voids that contain very few galaxies. The filaments connect at nodes where superclusters form. The walls and sheets of galaxies we have discovered in the zone of avoidance are part of this larger web structure. Understanding this structure helps us understand how the universe evolved from the nearly uniform state we see in the cosmic microwave background radiation. Shortly after the Big Bang, matter was distributed almost uniformly throughout space, with only tiny fluctuations in density. Over billions of years, gravity amplified these tiny fluctuations. Regions that were slightly denser attracted more matter, becoming even denser. Regions that were slightly less dense lost matter to their surroundings, becoming voids. This process created the web-like structure we see today. The structures hidden in the zone of avoidance are critical pieces of this story. They show us that the web extends continuously through space, even through regions we cannot easily observe. They confirm that the principle of isotropy holds true. The universe really does look the same in all directions once you account for our observational limitations. The gap in our maps was not a gap in reality. It was simply a limitation of our viewing position. These discoveries also have implications for dark matter research. The visible galaxies we observe represent only a small fraction of the total mass in these superclusters. Most of the mass exists in the form of dark matter, which does not emit light but reveals itself through its gravitational effects. By mapping the visible galaxies and measuring their motions, we can infer the distribution of dark matter. The structures in the zone of avoidance help us create a more complete picture of how dark matter is distributed in our local universe. The work of mapping the zone of avoidance continues. Despite the remarkable progress made with infrared and radio telescopes, there are still regions that remain poorly mapped. The absolute center of the Milky Way, where the supermassive black hole Sagittarius A times resides, remains particularly challenging to observe. The concentration of stars and dust there is so extreme that even radio waves struggle to penetrate effectively. There are undoubtedly more discoveries waiting to be made. Future telescopes will continue to push the boundaries of what we can see. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built. It will be able to detect hydrogen signals from galaxies that are currently too faint to observe. This will allow us to map the zone of avoidance in even greater detail. Space-based infrared telescopes, free from the interference of Earth's atmosphere, will provide clearer views of the dustiest regions. Each new observation has the potential to reveal another hidden giant lurking in the darkness. The story of the zone of avoidance teaches us an important lesson about the nature of scientific knowledge. Our understanding of the universe is always limited by our tools and our perspective. What we can see depends on where we are and what we use to look. For centuries, the zone of avoidance appeared empty because we were looking with the wrong eyes. Once we developed new ways of seeing, the emptiness filled with structure. This reminds us to remain humble about what we think we know. There may be other blind spots in our understanding, other limitations we have not yet recognized. It also demonstrates the power of human ingenuity and persistence. Faced with a seemingly impenetrable barrier, astronomers did not give up. They developed new technologies and new techniques. They found creative ways to work around the limitations imposed by nature. The story of mapping the hidden universe is a story of problem-solving and determination. It shows what we can achieve when we refuse to accept that something is unknowable. The zone of avoidance also reminds us of our place in the cosmos. We are not objective observers floating outside the universe looking in. We are part of the universe. embedded within it. Our location within the Milky Way shapes what we can see. We are like cartographers, trying to map an island while standing on the island itself. Some parts are easy to survey, others require us to climb mountains or cut through forests. The map we create reflects both the reality of the terrain and the constraints of our position. Understanding these constraints is part of understanding the universe itself. Looking forward, the continued mapping of the zone of avoidance will help answer fundamental questions about cosmology. How did the large-scale structure of the universe form? How does gravity shape the distribution of galaxies over cosmic time? How much mass exists in our local universe, and how is it distributed? Each hidden galaxy we discover, each supercluster we map, brings us closer to answering these questions. The blank spots in our maps are becoming filled with data, and that data tells a story about how the universe works. The discoveries of the Vela Supercluster in the South Pole Wall have shown us that even our local neighborhood holds surprises. We are still exploring our own cosmic backyard and finding things we never expected. This should inspire a sense of wonder and curiosity. If structures this large can hide so close to us, what else might be waiting to be discovered? What other blind spots exist in our knowledge? The universe continues to surprise us. Even after centuries of observation and study, the zone of avoidance is gradually shrinking as our observational capabilities improve. What was once a vast unknown territory is becoming mapped and understood. But this process reveals a deeper truth. Every answer we find leads to new questions. Every mystery we solve opens up new avenues of inquiry. The more we learn about the universe, the more we realize how much we still have to discover. The hidden structures behind the Milky Way are now revealed, but they connect to even larger structures beyond. The cosmic web extends far beyond our local neighborhood, and we have only begun to trace its full extent. The story of what was hiding in the zone of avoidance is ultimately a story about sight and blindness, about limitations and transcendence. We were blind to a significant portion of our universe, not because it was inherently invisible, but because we were looking in the wrong way. By changing our perspective and developing new tools, we gained sight. We saw what was always there, but had been hidden from view. This is the essence of scientific progress, finding new ways to see, new ways to understand, new ways to reveal the hidden structure of reality. The massive structures lurking behind the Milky Way are no longer mysteries. They are now part of our cosmic map, part of our understanding of where we are and how we move through space. The gravitational pull that has puzzled astronomers for decades now has an explanation. The missing mass has been found. The zone of avoidance has given up its secrets. But in doing so, it has revealed just how much more there is to discover. The universe is larger, more complex, and more structured than we once believed. And we have only seen a fraction of what exists in the darkness between the stars.